Hi all. My name is Alex or Sasha Lambov, as you prefer. I represent Grid Dynamics today, as you see. We will be talking about Rust as a cross-platform tool for implementation of business logic, cross-platform business logic for desktop and mobile operating systems. Few words about myself. I started as a non-IT switcher. Originally, I was iOS developer, started in age of Objective-C. In my career, we supported apps with over 25 million daily users. And last but not least, I was top 10 at the Republican Computer Science Olympiad in high school. Like, that's important for me, let's say. Let's dig in. What we'll be talking about more in details. First of all, we would be talking about the problem we try to solve. How basically to implement the backend locally. We will talk about options and alternatives, what we consider it, why we selected Rust, how we was thinking about that, and we will talk about how we assembled the pieces, what we achieved, what were the problems, because there is no development without problems for sure. So, what was the issue? What was the requirement? Like in 2020, a client approached company with the following request. We want to build a B2B platform, software as a service, which would consist of different products which would share the same business logic. The operating systems, we knew them. It should have been like, let's say, all desktop and mobile, major platforms. So Linux, Windows, macOS, iOS, and Android. But there was a catch, the issue, as being software as a service for big corporate users were not willing to send the data we would be working with. So we needed to work in technical terms with image processing and basically metadata over images. A tree of the elements of UI interfaces of their mobile apps. By no means they were not sending that to our service. And you see, like the clients, they were okay to send only usage analytics and licensing keys. So quite a restriction, you know. Our first way of thinking was to build, let's say, a box server, but it was hard to set up. It was not convenient. So we ended up that we would need to embed business logic core. Hopefully, that was not very big in functionality. I mean, it was quite complex, but not very large. Into the products itself, where we would ship as a binaries. The products, they should have been like desktop application and a bunch of SDKs for different systems. And one more thing, ideally, we wanted to have our know-how on our side, not to expose our code. So binary was the matter of choice. Okay, what was our way of thinking? Or what should we do in such things? Yeah, first alternative we was thinking about was Java. Yeah, stable system, enterprise, everything is clear how to do that. Yeah, but there were issues. First of all, it needed JVM to be installed. More friction on JVM. And the most important, there is no JVM for iOS due to licensing reasons. But we needed iOS. It was one of the key platforms for us to support that. Why Apple doesn't allow any code interpretation, almost any code interpretation for iOS? That's because Apple is paranoidly against users downloading apps in any form from other sources than App Store. So if you have code interpretation, you technically may build some app which would be in essence a third-party App Store with some downloading functionality. That's explicitly forbidden by Apple rules. Interestingly enough, we are not failing on that rules, like on that clauses. But because of that rules, nobody built something like that for interpreting languages. So Java was out of option. Next, what is allowed to be interpreted on iOS platform? Let us say it's JavaScript. JavaScript is an exception from that rules. And there is JavaScript, there were JavaScript engines for iOS, at least in these times where we were thinking about like late 2020, early 2021. But you know, as we discussed, the code is visible. It would be hard for us to obscure our algorithms, even if we use obfuscation. Second, execution is relatively slow. We had the parts with image processing. It was not the main reasons we rejected that, but we decided not to follow this path. Next, Python. Very nice language, very good for the things we needed, all algorithmical tasks. Everything okay, but there is no decent Python interpreter for iOS. For the same reason, there is no JVM for iOS. That was out of option, unfortunately as well, but we really wanted Python because it was very, like, it have been very convenient. Next alternative, in 2020, Kotlin, a new programming language, Kotlin, mainly Kotlin native. We're thinking about Kotlin native, built by Google, like supported, backed by Google. Major, like it worked for many of the platforms we wanted, but unfortunately it has, and even now it has, weak Windows support outside of JVM solutions. For Kotlin native, Windows support is tier 3. Even now, it's too low for us. We could not build a reliable thing of barely supported style and platform. Okay, we started thinking, okay, why are not going hardcore? Like old, pure, proven C or C++. It would work on every platform we wanted. We knew that from start, but it has manual memory management, it's low level. Team considered that to be too low level to work with. Team objected. They said, like, we don't want to work with that. I was not in that camp, but if majority of the team says, like, we are not willing to work with that, you better not object, like, you better listen, because maybe there are deep reasons for that. So, and after that, a guy on front end says, oh, why don't we try a new fancy language, Rust? We looked at that, and we understood that this is the technology we need. Why we thought that? Let us see in details. Here you see the mascot of Rust community, Ferris the Crab. So, but let's discuss what Rust is. First of all, Rust was designed in mind to be a system programming language. What does that mean? That means like that Rust was designed to be possible to build parts of operating systems in Rust, including kernel modules. And it proved to be correct because Linus Torvalds, by himself, recently allowed Rust code to be merged into like Linux code based, and part of Linux code based currently is written in Rust. Efficiency of the Rust is in the same league as C, C++, sometimes higher, like runtime efficiency, sometimes lower. Rust has higher level of abstractions than C and C++. That's easier to read and easier to comprehend if you're coming from more high level of abstraction languages. It has automatic memory management, but doesn't have garbage collector. So what does it mean? There is a borrow checker system. You have rules to write the code. When you follow that rules, compiler in compile time automatically deduces the places where some variables should be freed, and under the hood frees that, puts a calls to free that in the variable would be free entity in heap would be freed in runtime. One more thing, Rust is very secure by design. This allows developer to shoot it his own thing. Like, funny fact, when I was with my Swift experience, I was trying to write a production grade singleton in Rust. It took me like around a week. Not pure development time, but generally around a week. Why? Because Rust forced me to make that singleton thread safe. Why thread safe? Because it's part of the library. You have no guarantee, even if you know that your product would be single-threaded, generally you have no guarantee that your code would be executed from the same thread. So if you have a singleton, that should be thread safe, and that meant like that I need to learn all the threading systems of Rust. Okay, now let us discuss how we assemble the pieces. Here you see the abstraction of, let's say, our code base. We have a small C++ part which embeds like image processing library, Tesseract, industrial standard. We could not avoid that. Main of the logic is embedded in Rust core, in Rust code. That code is bound with C++ code. So most of the value is there in business logic terms. Around that, we have a thin layer of Rust bindings, a part of the code which binds the Rust code with end product programming language code. This part is very thin. You see, like in circles, it's more thick, but that's because we just needed to put wordings there. In reality, it's very thin. And we have around that end product programming language code base. For us, it was Java, Kotlin, Swift, JS, and now recently we added Python for that. Yeah, that's interesting. That's quite complex, but now we have around 12 products which share the same core. So we save a lot of development time by doing that. Let's see how we deliver. For understanding our delivery process, what we could say about that, let us say that we have two main repositories. We will take one single product and have an example of that, how we deliver on that product. We do that for different products. First, we have a Rust repo, which is common for all the products. And we have an end product repo, which is different per product. So let us have quite a real case when we need to change some functionality in Rust repo and multiply that around all the products we support. How we do that? First of all, we implement change and open a PR in the Rust repository. Like, that's all classical. PR gets reviewed. It gets QA'd. For small changes, it gets QA'd automatically. On this stage, we assure that the code would have correct logic, and the code would be compilable for every platform we use. So in some cases, we do manual QA on this stage as well. We have unit testing, integration testing, and sometimes manual, yeah. We merge that after all the pipeline was passed. So we merged that. Let's assume that we merged few PRs, and we want to have an internal release with that functionality. So what we do, we just put tag on a commit on master branch. Tag semantic version tag, this is the procedure of our release. Very simple. Yeah, and like what we do next. So that tag gets into bindings in end product repository. We update the bindings. If some API changes, we update beside the tag, we update the API as well, and we open a PR. We do review PR. We do QA, the same automatically, and in this case, there is more manual testing involved. We merge that. When we have merged everything we want for the next public release, we do public release automatically by our CI/CD pipelines. They compile the artifacts. For desktop application, they are posted on portal, client's portal. For SDKs, in binary form, they are posted to standard package managers. For iOS, it would be Swift Package Manager. For Java products, it would be Maven. It depends per product. Roughly is that. Okay. So let's say what we achieved here. First of all, we managed successfully to share business logic in Rust. And that business logic contains data processing, sending analytics data, networking, and WebSocket server. That was a success for us. On terms of operating systems, we support 5 of them, as I was told. Linux, macOS, Windows, Android, iOS. I would say that now, especially from the beginning and now, for all the operating systems, Rust works flawlessly. We have very little issues when we do compile something for one operating system and it's not working. Like we do write something for one operating system and that's not working for other. I would say like if you write decent Rust code, there is 99% probability that would work for all the variations. So that's good for us. In terms of operating system, because Rust is heavily, it's a quite low level. Rust is binary. We support 12 Rust targets. On Rust target means a combination of operating system, CPU architecture, and toolchain. Every of that components changes the binary. So we support 12 targets. For example, iOS consists of 3 targets, one being like modern, real device iOS on ARM64, other being simulators which run on Intel Macs. Third is there are simulators which run on Mac M1s, which are ARM as well. Like this is all different. For Linux, we support 2 architectures, Intel and ARM. For Windows, 1. For Android, I would say I don't remember them all. There are 4 or 5 mostly used architectures because Android phones, they have a variety of that. In terms of integration, we successfully integrated code with JS, Java, Kotlin, Python, and Swift. And we have CI/CD pipelines with unit and integration tests, and we even have end-to-end testing, more changes. Like we plan to introduce that. If you're testing Rust, if you are having Rust change, you should automatically test around all the platforms and products. But it was not without issues. Let's talk about them. First of all, Rust has very steep learning curve. It is hard for juniors or even some middles to become proficient in Rust fast. Main issue there is borrow checker. Because borrow checker, why Rust used that system instead of garbage collector? Because the same goal to be a systemic programming language. Garbage collectors, they are unpredictable in runtime. They might start in one moment, in next iteration or next run it might collect garbage in different moment. That is unacceptable for operating system cores. You could not do that, but Rust has that ambition to be a systemic programming language. We don't need that for our products, but we need to deal with that. Second, Rust is non-C derived and non-OP programming language. It's harder to transfer experience. It doesn't have classical inheritance. It has some concept of interface which is called traits. So you could transfer, but only part of the experience. a lot of approaches from Java, for example, or Kotlin, are not so easily transferable to Rust. So you need to relearn a bit. Next challenge we understood like in the process, it's labor market. Rust is a new hot technology. The demand is very high. The demand was skyrocketed by blockchain projects in their prime, because a lot of blockchain architecture is written in Rust. By different reasons why we choose Rust, but we need to understand that we have a competitor and salary expectations of developers are really high. So what we did, like we started to relearn our existing developers into Rust, and that proved to be more efficient, to be sincere. Development time. You know, when managers understand that they have a working cross-platform solution for all the products, sharing the business logic, they expect that if you have a change, that should appear like that, magically in all the products. Rust is binary. It's not like that. In reality, development time is somewhere between C++ and Java. It's faster than C++. I would say like it's slower than Java. One more thing, Rust is, for me at least, it's very easy to read, but it's very hard to write because of strictness of the compiler. Like really a challenge for junior mid-level developers if they see that first time, but that's achievable. Next, like most unexpected reasons for us, DevOps were not interested in our projects. Why? We have a really complex and pipeline, but there's no Kubernetes there. There's no Terraform. There's no site monitoring. We have boring shell scripts because Rust compiler is command line tool, and there are a lot of shell scripts. And DevOps, they are not interested in doing that. They consider that would be like a deviation from their career plan. How we pass that? We are not asking for DevOps. We are asking our Rust developers to learn DevOps procedures. That's more efficient and that's more fast. Okay, so let's summarize what we have there. So Rust for us has proven to be a valuable tool for sharing business logic, especially from technical side. We have almost no technical issues for us now when we learn how to do that. Majority of issues then non-technical, labor market, development time, something like that. About my main competitors, I would say like they're C, C++ for our use case, and Kotlin. C and C++ might have advantage in a pool of developers because there are more. It has a disadvantage of the development side. Kotlin has a advantage in terms of speed of writing the code because of garbage collector. Rust is somewhere between, but Kotlin has disadvantage in supporting platforms. So when you choose tool, something like that, you should really choose carefully and select the tool you need. I personally really like Rust. I think that with time, that programming language would gain more and more popularity because like that's improved C, C++ very much in essence. Basically, that's all we wanted to share with you today. And let's say we have a time for questions.
Hi, Alex.
Hi.
So I have two questions.
Yeah.
I saw on your Rust core you use network and WebSockets. So my first question is, what async runtime do you use? Because there's a problem in the Rust ecosystem related to async runtimes. And my second question is, did you consider compiling to WebAssembly?
Yeah, really good questions. Indeed, Rust has no runtime built in the language, but there is a basically what is Rust like? weak point for now, standard library is not so vast as in C++. So for WebSockets, we use standard library built around Tokyo library. Like Tokyo is a standard runtime for us, and that works for us. About WebAssembly, indeed we did that, but when we needed to replicate the logic for iOS, we understood that in the times there was no good WebAssembly interpreter for iOS. So we get native, and I would say like and we get native even for products which initially were WebAssembly, and I would say like we had a gain in speed of execution from 2 to 4 times facing WebAssembly. Yeah.
Okay, thanks for the question. We have the time for one more.
Hi, thank you for the presentation. It was really interesting. So my question is, are there like any frameworks which can facilitate the development of REST APIs on Rust? Like, for example, if you are a Java programmer or a .NET programmer, so like, is there a way to really enhance your skills in Rust? I mean, like in the direction of development of REST APIs and so on, like client applications.
Okay, client applications. Okay, so there are some tools like this is not our main case, because in our case we have 2 or 3 API requests, and they are not essential. Like that's analytics, they're checking licensing information, like that. But we do that. There is a standard library, I forget, like request with W, REWQS. We use that. That's kind of standard library. You could do that. Yes, for sure.
Thank you. Thank you, Alex.
Thank you.
Thanks for your performance.